Hey there, here's a recording on the remaining part of the section 2.2 notes. So here we are in the middle of page 6. And let's just recap example 15. So example 15 was asking us to find the vertical asymptotes for that function. So we drew a sign chart, we evaluated what happened at different intervals, and we noticed that the signs changed at -3 and +3. But it did change for the denominator. So when that happens, that should give rise to a vertical asymptote, especially if you were to plug in numbers close to -3 on each side or +3. Now let's take a look at a couple other examples. What if we got this one here? Well, if you do a sign chart again, so we have -7 and -3 and 2. And if you were to test out, say, +3, you can see that y is positive. And the signs will alternate when you have all linear factors, which we have here. Now, of course, we're going to see a sign change at 2, and we see another sign change at -7. And they do make the denominator 0. So in this case, we have x equals 2 and -7. So is there always a vertical asymptote when the denominator equals 0? The answer is really going to be, well, not always. We're going to say no. Not always. Sometimes. That might be a better way of saying it, but not always. But in this case, we did get one. But for the second function, we have two of the same factors, which actually cross off. But if I didn't cross them off and just did a sign chart with -7 and 2, and let's test like 3, for example. So it's positive. Then if I test 0 out, it's still going to be positive. We don't see a sign change here. That's the main reason why, well, I don't say main reason why, but it's another reason why we're not going to see vertical. Well, I mean, I guess you could have positive and positive, so I should actually take that back. But we do see that -7, that we're going to see something kind of like this here. But at 2, it's going to be a hole instead. And the hole is going to be at -1/5 if you plug 2 in into the simplified form. So you're going to have a hole if you kind of keep going down in that direction. I believe that's correct. I might have this actually in the opposite direction the more I think about it, but I'm not 100% sure. But anyway, the only vertical asymptote here is going to be at x equals -7. So that's what, it's x plus 7. Oops, sorry. So it's actually 1/9. My bad. Yeah, I knew that didn't make any sense. Let me backtrack a little bit. Yeah, so that'd be a 1/9. So that's what happens there. So do factor, do simplify. If factors cross off, those are going to give rise to a whole. And after that, then whatever makes the denominator 0 would be a vertical asymptote after you simplified. But doing a sign chart could also help too, and then determining whether it's going to be negative infinity or positive infinity on each side of the vertical asymptote. Squeeze theorem. So sometimes it's called the sandwich theorem. Not sure why they call it the 2 policemen and a drunk theorem. Maybe because 2 policemen are arresting a drunk. I don't know. But here's how it works. Let's say you're looking at f of x, and you have 2 functions that you know is less, one's less than f of x, the one's bigger than f of x for all x values except for c in some interval including c. And if the limit of g of x and h of x for x approaching c happens to be the same number for both, then the limit for f of x will also be that same limit. And this could also work when x approaching infinity or negative infinity. So let's actually look at an example of how this could work. So here we got a really funky graph. x to the 4th power times sine of 1 over x. Now, if you were to plug in 0, you would have a problem. You have 0 to the 4 power, and you have this. Now, this is kind of weird. I know that's 0. This is probably going to be a D and E situation, because if you actually were to graph y equals sine of 1 over x, the problem is that as x gets really, really small, this gets close to infinity, but the problem is that sine's going to keep oscillating as you get closer and closer to 0. So you really just don't know what's happening there. So we can't really use our limit theorems, but the squeeze theorem can actually help us out. And here's what you're going to do. So we do know that sine of 1 over x is in between these two numbers. So think of this as the g of x, the negative 1. Think of this as h of x, positive 1. And think of all this as the f of x. Now, what if I multiplied everything by x to the 4 power? Then this is still a true statement. Now, multiply everything by the same thing is fair treatment. Okay, so this is true. I know this is true. Why not that be true if I multiply everything by x4? Well, the thing is that the limit as x approaches 0 of x to the 4 power, I know is just going to be 0, because x to the 4 power is just a simple polynomial function. You can just plug in 0 and you get that. The limit as x approaches 0 of negative x to the 4 is also going to be 0. You know, that just goes down, but still you could do straight up substitution. So if both those limits exist, where the limit, and by the way, my g of x does change now. Now it becomes negative x to the 4 and x to the 4. And now that's my new f of x. So if this limit obviously is 0, and this limit's obviously 0, then this limit of this function here will also be 0 due to the squeeze theorem. So that's the theorem that we can use that will be reliable. So it's basically you're squeezing it in between two functions here. So assuming that you have one limit, you have one function that is less than this and less than that, and both these limits are L, then this one's also going to be the same thing. Let's keep moving here. Let's try this one. Now, in this case, x approaching 0 again, we have x cubed, and we did have to be careful with the algebra, and you'll see why in just a sec. So we know that this is a true statement. And I multiply both sides by x cubed. Oops. I'm not supposed to have that there. Now, because x approaching 0, your left-hand limit is going to involve negative values. Right-hand limit is going to involve positive values for x. We had that happen up above, but you're doing x to the 4 power, so there's no sign change. There will be a sign change, obviously, when I have a negative x value. So when you have negative x values, actually, things are going to change direction. If I have negative x values, then this actually becomes a positive. This is the limit as x approaches 0 from the left. And that's going to switch also, because then that also becomes negative. Over here, it just stays as is. That's the limit as x approaches 0 from the right. But regardless, if I do the limit as x approaches 0 from the left of x cubed, or negative x cubed, you're going to get 0 for each of those cases. And likewise over here. If I do limit as x approaches 0 from the right of x cubed, or negative x cubed, you get 0 in that case as well. So in this case, the LHL equals RHL, so the limit of this will just be 0 by the squeeze theorem. So again, the way the squeeze theorem works is you do need to find two functions, one that you know for sure is less than what you're looking at, one is greater than, and sometimes you could look at a part of it, and then introduce the other part by multiplying all sides by that, so you maintain this inequality. And then take the limits of these outer ones, and if those limits equal the same thing, then that limit's also going to be the same thing as well. So hard to kind of visualize this. I'm trying to wrap my mind about how we can actually visualize to really understand what's happening here. But it is something that does hold true. I mean, you could, if you wanted to, plug in numbers close to 0, or look at this graphically, the whole thing. You could do that too, but it is a theorem that actually works. Proving the theorem, I will be honest, I haven't proved this theorem before, so I would have to look that up, but it's something that we can use to kind of help us out for tough limits like this. Lastly, example 18. Fortunately, we have one-sided limit, x approaching negative infinity, so that's fine. You have sine x over x. Again, you can't really plug in negative infinity because this will oscillate. And of course, this will just go towards negative infinity. But what we could do, we could just focus on sine x. I know sine x is in between these two numbers. And if I multiply both sides by 1 over x, or all three sides, I guess, negative 1 over x, fair treatment. Now x is going towards negative infinity, so actually these do need to change direction. So, but not a big deal. We don't need to really worry about that. But the thing is that the limit as x approaches negative infinity of 1 over x, or even negative 1 over x, are both going to approach 0. And so by the squeeze theorem, this limit as x approaches 0 of sine x over x will be 0. So there we go. There's a squeeze theorem. And I'll be assigning some homework in just a little bit, or textbook prompts, I guess. All right, see you later.